formula that we have in that particular case is, let me just get the formula here for us. Okay, so I'll just move all these over. Yeah. So our formula here is, let's say, RS is simply equal to 1 minus 6 times the sum of the distance between the ranks. So both variables are rank ordered. Okay, don't forget. So what we do is we calculate the distance, the difference between the ranks of the x's and the y's to give us our d values. And that's divided by, and then we square them, divided by the number of paired observations times the square of the number of paired observations minus 1. And I have a video on how to calculate the Spearman rank order correlation coefficient, and maybe you can have a look at that. You can have a look at that later. The next correlation coefficient that's actually important for us is when we have a multichotomy and a multichotomy. So in that particular case, so we're talking about a multichotomy. This is Kramer's V. So we're talking about Kramer's V, which is for a multichotomy versus a multichotomy. Okay. And the formula that we have is either C, let's just call it C for Kramer. C is equal to the chi-squared value associated with the contingency table. Okay, so we have a multichotomy, so we have the x's and we have the y's, and we have a number of levels on the x's, and more than 2 levels on the x's, and we have a number of levels on the y's. And what we do is we calculate the chi-squared, let's say, test statistic for that particular contingency table, and we use that value divided by the total number of observations. So we have n plus the chi-squared value, and it's the square root of that. Okay, so to calculate Kramer's V when you have a multichotomy and a multichotomy effectively boils down to actually calculating the chi-squared test statistic, the chi-squared measurement between both of those particular variables. Okay? But anyway, there's the formula. If you want to know how to calculate chi-squared, I would recommend that you have a look at one of my previous videos, which actually walks through the actual calculation of the chi-squared test statistic. Let's have a look now. So say if we're dealing now with a dichotomy, a natural dichotomy and a dichotomy, we have the phi correlation coefficient. Okay? That's for a dichotomy versus a dichotomy. Okay. So there's Kramer's V, and in relation to phi, we have phi is equal to. Now keep in mind that this is a dichotomy. 2 variables, our x's and our y's, are dichotomous. So effectively, what we have is we have our x variable that has 2 levels of measurements here. Okay, and we have our y variable that also has 2 levels of measurements, which gives us a contingency table with 4 cells. And let's call this A, B, C, and D. This could be, let's say, it's a dichotomy. It's probably artificially labeled as 0s and 1s and 0s and 1s. Okay. But each cell A represents the frequency. How many paired 0s are there in the data set? How many? B represents the frequency of 0s and 1s. C represents the frequency of 1s and 0s, and D represents the frequencies of 1 on an X, the presence of the condition on an X, and the presence of the condition on the Y. Okay, so that gives us then our phi correlation is effectively AD minus BC. So it's the product of the frequencies along the diagonals, the difference in the product of the frequencies along the diagonals, divided by the sum of the frequencies on the rows, the product of the sum of the frequencies on the rows. So it's A plus B times C plus D times the product of the sum of the frequencies on the columns. So it's A plus C is the sum of this column, and B plus D there. Okay, and it's the square root of that particular calculation. Okay? So this is quite similar also to the chi-squared test statistic. Actually, the correspondence is that chi-squared is actually equal to n times phi squared, if I'm not mistaken. Okay? But effectively, to calculate the correlation between 2 naturally dichotomous variables, we'd calculate the phi correlation. And all it requires is us to do is to build the contingency table, to observe the frequencies within each cell. The frequencies are labeled A, B, C, and D, and to use them frequencies in the calculation. So what I've presented so far is our four, uh, let's say, typically, typical correlations that you would find in most textbooks: Pearson, Spearman, Kramer's, and phi. So let's have a look now at the point-biserial and also eta in relation to a dichotomous and an interval variable, and a multichotomous and an interval variable, to see what they look like. So let me just move these over here. So what I'm looking at now is the point-biserial correlation. Okay, so the point-biserial. So we have the point-biserial correlation coefficient, and that's when we have a dichotomy versus an interval, okay, stroke ratio scale variable. Okay, so let's have a look at them two there. So we have our point-biserial, and the correlation coefficient is R subscript PB for point-biserial, and it's equal to. Let's keep in mind that we have our two variables. We have our x variable and our y variable. X is the dichotomous variable, so let's say we have 0, 0, 1, 1, 1, 0 as an example, and y is an interval variable. So maybe this is a measure of salary, or let's say time. I don't know. Let's say 2.2, 2.7, 2.5, 3.2, 8.2, 6.7. But effectively, what we have is we have two different groups of people. We have those that are coded on as a 0 on the dichotomy, and those that are coded as a 1 on the dichotomy. And the point-biserial requires that we calculate the average value, okay,